All right, what we're gonna first start with, keeping everything as routine as possible, we're gonna do one of the finals first, and then we'll open it up for questions. There are two test 2 packets. This one this is the test 2 from the spring, and what we'll do is we'll go through multiple choice and the problems, and we'll do the other one tomorrow. Same rules as before. Test 2 is Wednesday, 10 to noon. Same thing as before. Madison Vick, I sent an email to the office about because you're not Madison, the one behind you. The office, I've let them know. So after lecture, probably this afternoon, go to them and say, because I thought I confirmed you. It may be something, there may be some glitch somewhere. So, same as before, all sorts of information given. None of it's really labeled. The most appropriate letters are given, and then you can figure the rest out on your own. Let's do multiple choice. Ooh. Second is a unit for period. Frequency, what's the unit for frequency? Hertz. What's the unit for momentum? Kilograms meters per second, yes. What's the unit for energy? Joules. What's another way of saying joule? Newton meter. What's another way of saying joules or Newton meters? Kilograms meters squared per second squared. Yes. Now some of these, I'm going to go through and make sure they don't have the error, because I think one of these do. Circle rotates 3 times in 2 seconds. What is the period? Or 3 times in 6 seconds. I Freudian slipped it and gave the answer away. It's 2 seconds. N is, or actually, the period T is the total time, little t divided by N. We've discussed this. Unit for period is second. What's Newton typically used for? Or what does it? Newton is the unit for X. What's X? Force. Good. Now I love these questions. I came up with these. You are walking on a disc that is spinning at a constant rate. As you walk further away from the center, which means that the disc is rotating like this and you're moving like that. As you walk further away, what changes? The radial acceleration. Because it's a constant, it is not changing its angular velocity. Omega isn't changing, frequency isn't changing, the period isn't changing. But as you move away, your radius is, so your radial acceleration is changing. What are the units of the coefficient of friction? Blank. No units. Occasionally, it's the one where I say, actually, it showed up on test 1. Coefficient of friction, think grasshopper, kilograms meters per second divided by newtons or something. Which expression represents the unit of work? So the Newton meter. In an Atwood's machine, do the 2 masses have differing velocities? No. Not in ours. Now, number 8, we're going to stick with this for a moment. The fraction of energy, let me blow this up. Fraction of energy remaining is what? D. D is the energy remaining. If you wanted to convert it to a percentage, you would just multiply by 100. What is the energy lost? Which one of the the remaining 3? The fraction of energy lost. Now, B is the initial energy over the final energy. So that would be a ratio, that would be a weird ratio. If you know that the energy remaining fraction is this, it's actually C. Now this is small print and it may not show up well on the up on the thing. Whoa. So D is energy final over energy initial. So 1 minus, ooh, hold on. Oh wait, I know. We've had a mechanical error. So 1 minus the energy remaining is the fraction of energy lost. The units of energy are, okay, and we've discussed that. Kilograms meters squared per second squared. You move a box across the floor. The change in potential energy is what? 0. If there's no change in height, there is no change in potential energy. The units of radial acceleration are what? Meters per second squared. Blank over second squared are the units of what? Angular acceleration, yes. It's because technically radians is not a unit. Inelastic collisions conserve A, only momentum. Excellent. Now, number 13, I've had to edit it over the years, but it's a little, wait, not that one, this one. Thread is being pulled off the spool. The spool revolves at a constant rate. Which of the following is false? Radial acceleration equals 0. If the thing is rotating, the radial acceleration has to be non-zero. If it moves at a constant rate, you immediately know that alpha is equal to 0, d omega dt is equal to 0. You also know that AR and V at the edge are greater than 0 as well. So, number 14, rotational mass is what? Rotational mass is what? Yes?
So, knowing if alpha is 0 or not 0, is that by like if acceleration is at a constant rate, then we know that alpha is 0?
Choose the word. If you said angular velocity is constant, then alpha is 0. The words that came out of your mouth were, is if angular acceleration is non-zero, then yes, alpha is non-zero. So you gotta choose your words. I know what you were saying, but you said it the wrong way.
Got it, thank you.
Okay. Circle rotates 8 times in 4 seconds. What is the frequency? 2 hertz. Oh, we didn't answer your question, interrupted me. Rotational mass is what? Moment of inertia. You have a stick or a disc or some geometric shape not rotating at its center of mass. What theorem must you know? Parallel access. Not access. Well, you said it confidently, so I respect that. Axis theorem. Units of moment of inertia are kilograms meters squared. Yes. Now, let's go over this real quick. What's the moment of inertia of a particle revolving in a circle? mr squared. What's the moment of inertia of a disk rotating? 1/2 mr squared. What are the units of a stick? 1/12 ml squared. So everything is based on a unit of a mass followed by a unit of a distance squared. So kilograms meters squared. Those are the units. You are running around the circle. So you're running around in a perfect circle. You start to run faster. What does not change? The moment of inertia. So you can treat yourself as an individual particle moving around in a circle. Moment of inertia does not care about your velocity. Work has what units? Joule. Frequency is hertz. What are the units of linear momentum? Linear momentum. C. Linear momentum is mass times velocity. Mass, kilograms, velocities, meters per second. Translational equilibrium means what? Sigma F is 0. Sigma tau equals 0 is what? Rotational equilibrium. B is what? It's conservation of what? Momentum, linear momentum. D is what? What is L typically used for? Angular momentum. So it's the conservation of angular momentum. An Atwood's machine has no friction. Yay, no friction. What is the ratio of E start over E end? 1. Let's go, oh, hold on, let's see what we got else. All right, we can go over some other things. If Atwood's machine has friction, what is the ratio of E start over E end? Remember what I said. E start over E end. What ratio would it have? It would have to be greater than 1 because E end is less than E start. So a big number divided by a smaller number is greater than 1. You are walking on a disc that is spinning at a constant rate. As you walk further away from the center, what doesn't change? As you walk further away from the center of the circle, what doesn't change? So if you're walking further away, your R is changing. So your radial acceleration is changing. It's A, angular acceleration. The disk is not changing its rotation. If it was speeding up or slowing down, it would change. The angular acceleration is not dependent upon your position on the disk. Your radial acceleration is. Your moment of inertia and angular momentum are, but not angular acceleration. 24, A cross B is what? Negative of B cross A. 25 is so dull. Relationship between normal force and kinetic friction force is what? D. So some of the things that we do use in test 1 are used in test 2. Understanding friction force, normal force, energy removed through friction because of the friction force. So you're going to have to know a few of those things. All right, right-hand rule game. B cross D. F. Now, one of the things that a student brought this to my attention, I've heard of this before. The game that, when you've got the right hand rule game, all you got to really do is your right hand. And one of the rules of the game is I can't give you B cross B, or I can't give you, in this case, B cross E, because it doesn't really make any sense. And people have made the observation, if you've got B and D as your two vectors, A and E are eliminated. You can't have a horizontal vector crossed with something else and get another horizontal vector. So in the case of B and D, you've only got two choices, C and F. So in this case, B is to the right of the room, D is into the board, so that leaves F. C cross B. It should be A. C is towards the floor, curl B towards that way, thumb points out, and then that. Probably for you at your seat, when it comes to, I just put my hand towards the ground rather than just right in front of you, because it's a little bit, you're free to move your arm in any direction that you need to. D cross B, done. So D is into the page, B is to the right, so you get C. So A, E, A is out, E is this way, so probably I would have A, E, down is C. So you got C. E cross D, E, D, C. E, B, C. So let me get those out. I'll just do them again to show. So B, B, D, F, C, B, A, D, B, C, A, E, C, E, D, C. So they're repetitions. And one of the things that I stress, I'll stress it again, answers on this page will not be graded. For the right-hand rule game, take it, put it on a sheet of paper, put it right up front of the scratch work. Also, as a reminder, if this is your sheet of paper, avoid writing in the upper left-hand corner, probably with a radius of like 1 to 2 inches. And why is that? That's where your staple is. So if you do write up in there, the graders will pry your test apart and take a peek in there to see what's going on. But it frustrates them. And an angry grader is not a generous grader. So let's just make them happy. Keep the stuff out front. Stay away from the corner. All right. Oh, excellent. The Fisher Fury problem. Dun, dun, dun. Now, one of the things that we're actually going to skip, well, I'm going to run through all of them. They're pretty easy. The Fisher Fury, let's do this. And just as a hint, when we get to test 3 material, we will figure out why the Fisher Fury is called that. There's a reason. Some student finally figured it out. You have a disc. There's a bar on the disc. It is welded directly across so that its radius is, the radius of the disc is 1/2 the length of the stick. The stick's mass and the disc mass are given. The radius is given. The Fisher Fury grabs that line and travels at 10 meters per second and is constant. I must find alpha, L, and F. Alpha, angular acceleration, L, angular momentum, and F is the frequency of the disk. So the best thing that we have is that V is omega R. So if V is constant, omega is constant. Alpha, which is d omega dt, is 0. If omega is constant, its change with respect to time is 0, therefore alpha is 0. All Fisher-Fury problems since the beginning of the Fisher-Fury era, alpha has always been 0. If you've got a Fisher-Fury problem on your test on Wednesday, that alpha is 0. But I'd like for you to go through the motions and explain why. So that's alpha. Now that means V is omega R, so omega is V over R. Omega is 2 pi F, so F is omega over 2 pi. V is omega R, omega is V over R, omega is 2 pi F, so F is omega over 2 pi. So if F is omega over 2 pi, F is V over 2 pi R. So V is 10, 2 pi R is 0.4, and so whatever that number is. Or does anybody have a spare TI something? The ones that I typically use. Ooh, now remember, oh yeah, I really like yours. I will try to steal this, so make sure that you take it back from me. So the frequency is 3.98 hertz. That's the frequency. We have alpha. All we need is angular momentum, L. L is I omega, or L is I 2 pi F. So we can change that. So all we need to know is I. Moment of inertia is the sum of the moments of inertia. Moment of inertia of a disk is 1/2 mass of the disk, R squared, plus 1/12 mass of the stick, L squared. And so we get this. Plugging it in, 1/2. The disk is 2. The radius is 0.4. Mass of the stick is 3. L is 0.8. Frequency is 3.98. And I get, now you can tell I've been planning ahead with this. I get 8.00 kilograms meters squared second. So people typically write this as 4, and that's 8. And so that is problem 1.
How do you get L 0.8?
L as 0.8.
Or just where the
Oh, you mean where did I get that equation?
the one like where it's like 1/12 M mass of stick L.
Oh, the moment of inertia. Oh, that 0.8? Okay. Moment of inertia of a stick is 1/12 ml squared. The length of the stick is twice that, the radius. So the radius is 0.4, therefore the length is 0.8. And that's where the length comes from.
Any chance can you just show the problem?
Yeah. I showed it at the beginning. So problem 2, I want to know the mass, or I'm given the initial velocity of the machine is 0. The coefficient of kinetic friction is 3, mass 1 is 3, the hanging mass is unknown and I'm looking for it. I want to know that mass, and if the final velocity is 10 meters per second, what is the fraction of energy remaining? Fraction of energy remaining is E final over E initial. So I'm looking for this and that. And so that is the problem 2. Now, while we're looking at the problem, just so that people can get this, the thing that I'm going to do with this rotation problem is there's only 3 things that I'm going to do, or 3 geometric shapes that I'm going to use. Sticks, point masses, and discs. That's it. So the thing that you have to be familiar with is A, know how to manipulate those moments of inertia, and B, know how to manipulate them if you have to use the parallel axis theorem in order to get it. And so if you've got that stuff, you'll be ready. So the big variant that I can play with is what I ask for, and then just make that disc a little bit weird. Once you're familiar with the parallel axis theorem, it's not a big deal. So for this problem, I'm restricted to only using the equations of energy. So you've got the initial energy and the final energy. The initial energy is when everything is at rest, and so there is no kinetic energy, but the potential energy is M2GL. That's the whole potential energy. The final potential energy is when the mass is at the bottom. The kinetic energy is 1/2 M1 plus M2 V squared. There is no potential energy, so that's the kinetic energy at the end of the motion. The only thing that gums the works up is the fact that there is friction and it's moved over a distance L. So you have to go through the usual sum of the forces in y is equal to 0, which is equal to normal force, minus mg, or m1g. So normal force is equal to m1g, which means that friction force is mu sub k m1g, which means your work is mu sub k m1g capital L, because work is force times distance. So put the pieces together. Potential energy initial minus work is equal to kinetic energy final. Potential energy initial, M2 GL minus work, mu sub K M1 GL equals kinetic energy final, 1/2 M1 plus M2 V squared. So that's the equation put together. That's how you derive it. In all of these cases, you will basically have to derive this equation. Now comes the question, what am I asking for? Well, I'm asking for M2. I'm asking for the value M2. I have everything else. So now we're in just algebra mode. Solve for M2. First thing I have to do is I'm going to distribute this. I'm left with M2 GL minus mu sub K M1 GL is equal to 1/2 M1 V squared plus 1/2 M2 V squared. I don't differentiate the V's because the V's are the same. They both travel at the same rate. This means that M2 GL minus 1/2 M2 V squared is 1/2 M1 V squared plus mu sub K M1 GL. Just getting all my M1s and M2s on their respective sides. Mm-hmm. Sure. Yeah, let me give you the full sheets. Just because I don't like fractions, multiply everything by 2. This is an optional step. Next, factor out M1s and M2s. Oop. So that's a G and that's an L. Solve for M2. And so now you have a mass expressed in terms of variables that can be easily expressed. Now, one of the things that we could do is sit here and go, what units do we have? Well, mass is in kilograms. Velocity is in meters per second squared. G times L. G is meters per second squared. L is meters. GL, once again, meters per second squared times meters minus meters per second squared. They're all meters squared over seconds squared, so all of them cancel, leaving you with just kilograms, so it is a valid equation. M1 V10 plus 2 times 3 times 10 times 20 2 times 10 times 20 minus 10 squared. 660, 20 divided by 400 minus 100 or 300. So I get M2 is 4.33 repeating kilograms. And so that's it for that part. So that's mass 2. Yes?
Okay, so on the first step, after you go from potential energy minus work is equal to kinetic energy final, how do you know to use the the second mass for potential energy and the first mass for?
Well, in the picture, and that's one of the things that I didn't draw. The picture has M1 up top and M2 hanging. So the only object that changes its potential energy is mass 2. Now the reason why I have mu sub k m1 gl is that L is the distance that M1 moved across, because if M2 falls L, M1 moves L. The last part, energy remaining, I take the energy final and divide it by energy initial. The energy final is just 1/2 M1 plus M2 V squared. Energy initial is just M2 GL. So you don't have to work with work. So energy final is 1/2 M1 is 3 plus 4.33 10 squared over M2, which is 4.33 times 10 times 20. Divided by 2 times 50 divided by 4.333333 times 200, and I get a number that is 0.42, and that's it. Not very nice, but that's fine. So for the last problem, it's a problem that we've seen before. It's a problem that freaked everybody out because there's no fulcrum. It's not a big deal. It's the problem of the jump jet, the Harrier jet. You have 10,000 kilograms at this position. You have two jets, F1 and F2. Both of them are pushing up on the plane. The question is, what are the magnitudes of those thrust engines? The plane's not moving, it's not rotating. So what we do is we say that sum of the torques is equal to 0. Now I have to choose a rotation point that allows me to eliminate one of the forces of the engines. So I choose the physical location that is, I'll choose F1. So in this particular case, I've got an mg down, mass of the plane, and then over here at the front of the plane, I've got F2 pushing up. This gives me two torques, mgr1 and F2 R1 plus R2. The distance from this force of the plane's mass to the rotation point, which is at F1, its distance is R1, and the distance from F2 to F1 is R1 plus R2. We're treating the back of the plane as the rotation point. All of the forces are to the right. the gravity force is down. Thumb goes into the page, or negative. Force 2 is to the right, but force 2 is up. Thumb comes out of the page, or positive. So this ends up becoming mgr1 is equal to F2 R1 plus R2. mgr1 over R1 plus R2 is equal to F2. That gives me 10,000 times 10 times 3 divided by 3 plus 15. So that gives me 16,667 newtons. That's F2. Now for F1, we could do the same thing, sum up the torques, but the easiest way is to just say it's not moving up or down. So if it's not moving up or down, then the sum of the forces in Y is equal to 0, which is equal to F1 plus F2 minus mg is equal to 0. We solved for F2, let's find F1. mg minus F2 is equal to F1. So this gives me 10,000 times 10 minus 16 and 7 is equal to 83,333 newtons. And that's the force of the back engine, the F1 engine. And so that's the problem. And this problem here, March 30th, 2017, that was the date that a class had ever attacked that type of problem. Never been seen in problem sets, never been seen in a test. I told my father about it. He said it was evil, and I said thank you. But when you look at it, it's not that bad. You just sum the torques, sum the forces, done. In and out, give me my 15 points, thank you. And so this is not a bad test. I would say that the test is kind of on the weak side. I think for you guys, since you do have a full 2 hours, this problem, I wrote it because, another reason why I think it's kind of a weak test. And it's intentionally that way. Spring 213 is the weakest of all my courses. It's primarily exercise science students. You do get pharmacy and a few pre-meds. So what I tend to do is spring 213, I go gentle. But when you look at it, and so this is why I put in this one, because I was like, I'm being easy. I'm gonna throw that jump jet problem in there and see how it does. And that differentiated the people who understood the material from the people who didn't quite get it. And so that's it. And so that's test 1. Let's talk about the appetizer right-hand rule. I mean, that's 100%. That's in it. Get ready for it. The Atwoods with energy, that's another 100%. Then I've got, for 2 and 3, I've got rotation, alpha equaling 0. I've got rotation, alpha not equaling 0. So probably this is a combination of 2. For problem 3, the torque bar is just so darn good, which means to a lesser extent, I would probably a far less extent would be collision. But I think with Atwood's with energy, rotation, alpha equaling 0 or alpha not equaling 0, that's the one I think I'm really going to have fun with. And then the torque bar, I'm leaning towards away from the plane and then doing the conventional torque bar problems like this, which is problem set 6, back of the page. So stuff like this. So I kind of would keep track of conservation of angular momentum, conservation of linear momentum, and collisions from the perspective of multiple choice. But for the problems, also for the fact that it's summer and so we move so fast, torque bar, rotation, 0 or non-zero, and Atwood's machine with energy, those are the big guys. And then knowing right-hand rule game, and that would be enough. That would be more than enough. On the final, I think the final allows me to let a lot more of my personality come through, because then I got 3 hours for this great celebration. So that's when the collisions show up, is that. So, all right, we got another whole hour. What would you guys like to talk about? Pretty much anything you guys want. We're in review mode. The concrete has been poured. Now we've got 2 days to just let it set. So anything that you guys want to talk about? Yes? Problem set 6, number 1. Oh, so we're talking about the true problem set 6, not the fake problem set 6, which is problem set 5. You're talking about the one with the rebel rod and reel. Okay. All right, this is the classic, this is the Fish of Fury problem, really. The rebel rod and reel has 120 meters of line on the spool. So what happens is you cast 12 meters of line. The Fish of Fury, well, I'm drawing it opposite. Fish of Fury catches it, turns around, and starts speeding away at a constant 12 meters per second. So if you threw out 12 meters of line, it will run out at 120. So your initial X is 12 and your final is 120. It moves at 12 meters per second. So if the fish's speed is constant, how long will it take before the spool runs out of line? Classic one-dimensional motion problem. X equals X naught plus V naught T. There is no acceleration. It is explicitly stated that the fish does not accelerate. Well, it goes from 0 to 12 just instantly and then cruises at 12. I'm looking for time. X minus X naught, V naught T, X minus X naught over V naught is equal to T. So this means 120 minus 12 divided by 12. And that gives me 108 divided by 12, or 9 seconds. How many revolutions did the spool make when it runs out of line? So, if 12 has been cast and it started with 120, you only got 108 meters of line. So the number of oscillations is 120 minus 12 divided by circumference, 2 pi r. So you've got the total amount of line cast out. You've got the circumference of the line that's given out with each rotation. So this becomes 88 divided by 2 pi. R in this case is 4 centimeters, 0.04. Remember to convert to kilograms, meters, and seconds. And that gives you 88 divided by 2 times pi times point. What? When did it go 88? I don't know, because I lost my dang mind. 108. Never trust an old man. So, well, it would help if I inputted the right answer or right numbers. 108 divided by 2 pi. That gives me 429.7 rotations. What is the period? Now, what I'm looking for is period, frequency, and angular acceleration of the spool while the fish is pulling off the line. Which one is the trivial answer to give right now? Which one of those three? You can just state an answer. Alpha. What is alpha? 0, because omega is constant. And I would say alpha is 0 because omega is constant, and alpha is the change in omega with respect to time. Done. Now, we've talked before, period is the total time divided by the number of oscillations. Or you could say that the period times the number of oscillations is the total time. This becomes little t is 9, big N is 429.7. So that gives me, ooh, yay, I have the number in, divided by a second answer. And that gives me a period of 2.09 times 10 to the negative 2 seconds. And frequency is the inverse in period. So all I have to do is invert this, and I get 47.7 hertz. And that's it. The big problems: understand one-dimensional motion with no acceleration, understand that number of rotations is the length divided by circumference, understand that period is this and frequency is that. Yes?
Do number 7 on problem set 5.
Number 7 on problem set 5. Okay. So two masses are joined together by a massless rod of length 0.8. One is small, one is big. They are rotating about their center of mass with a period of 0.25 seconds. So period is 1/4 second, or 4 hertz. They're rotating about their center of mass. So remember when I taught you how to figure out center of mass for a set of particles, you take the weighted average. And so you can pick whatever point as the origin. You can orient this thing in any particular, in whatever fashion you wish. In my particular case, I put the small one on the left and I declare it to be at the origin. So to get the weighted average of this thing, the x center of mass will have the coordinate of the sum of the positions times their masses divided by the sum of their masses. This makes it x1 m1 plus x2 m2 divided by m1 plus m2. x1 0, m1 1, x2 0.8, because that's the distance between the two. m2 3 divided by 1 plus 3. So this is 2.4 divided by 4, or 0.6. So the smaller mass and the bigger mass, if that distance is 0.8, then that distance there is 0.6, and that distance there is 0.2. And so we have, the first part of this is to figure out where this thing's rotating. So it rotates at 0.6, which means that R1 is equal to 0.6 meters and R2 is 0.2 meters. That's the second object, that is the first. Now, what is their moment of inertia? The moment of inertia is the moment of the first one plus the moment of inertia of the second one. Moment of inertia of the first is m1 r1 squared, and then m2 r2 squared. This gives you 1 times 0.6 squared plus 3 times 0.2 squared. And I get a moment of inertia of 0.48 kilograms meters squared. Always be sure to include your units for a final answer. So that's the moment of inertia. Second part of the question is, what is their angular momentum? Angular momentum is I omega. Now, how do you get omega? Omega is 2 pi f, or since I used period, it is 2 pi over period. So this becomes I 2 pi over period, which means it's 0.48, 2 pi divided by 0.25. And so that is problem 7. Now for 8, to do number 8, I won't do the problem, but I'll tell you just what happens. In problem 8, I tell you that you drill a hole in the peg at dead center, and then the object rotates around that. So it rotates now like this. This means that R1 is now 0.4 meters and R2 is 0.4 meters as well. So to determine its moment of inertia, you just plug in different numbers. The angular velocity is still the same, so you don't have to omega doesn't change. All that changes is R1 and R2 for this situation. In problem 7, well, let's knock out the setup for 9. in problem 9, you still have the hole cut in the middle. That one is 1 kilogram. That one is 3 kilograms. The R1 is 0.4. The R2 is 0.4. But now you have a mass or a bar with mass. One of the things that we probably should introduce is the concept of linear mass density. We're all familiar with volume mass density. Volume mass density, or as we call just generic density, is rho, which is mass over volume. Linear mass density is lambda, or mass over length. So it's a different style of density. When is it really useful? For situations where you can more readily measure an object's length rather than its entire volume, like guitar strings or rods. So the mass of this object is lambda L, which are both given. L is 0.8, lambda is whatever I tell you to do. And then for 9, the moment of inertia becomes m1 r1 squared plus m2 r2 squared plus 1/12 mass of the stick L squared. And so you've got a new moment of inertia, and then you just run it like you do 7 and 8. Or actually, this is 10. In 9, you've got a mass, and really what you can do is so a stick with mass, you can convert it to a massless stick, but with a mass right at the dead center. So we can do it that way. So to find the center of mass, you treat that as the origin, x1, m1, plus x of the stick, mass of the stick, plus x2, m2, divided by m1 plus mass of the stick plus m2, where mass of the stick is lambda L, and then x of the stick is just L divided by 2, or 0.4. And then x2 is 0.8, x1 is 0. And so you can figure out the center of mass. So problems 7, 8, 9, and 10 are really an exercise of playing with determining center of mass and playing with the moment of inertia for various systems that look eerily similar. And it's all based on what the masses are and their orientation to the rotation point.
How do you make the stick of
How do I what?
How are you making that stick fast?
It is it's a simplification, because if you have a mass that's uniform, you're using your common sense, and you're going, well, where's the center of mass of that stick? Dead center. And so you can, in an effort to determine the center of mass, they're equivalent. Now, when you're working with moment of inertia, it gets a little bit different. But for just figuring out where the center of mass is, you can change that stick and two masses into two masses, massless stick, and a third mass that coincidentally has the mass of the stick from the previous part. It is this won't do it, but if I were to throw this, like, perfect demonstration. If I threw this at you, what would happen? It would rotate directly around the center of mass. So if I threw this stick at you and I threw a ball at you, they would both travel at you around their center of mass and come at you. It's if another way of demonstrating center of mass and how it acts like a point particle. When you watch Mike Myers in those Halloween slasher films, and he throws those 3D movies where he throws the axe at you. Well, what happens? Does it rotate around the dead center of the handle? No, it rotates closer to the handle of the system, or the center of mass of the system. Where you have the hatchet, that's the heavy mass. The stick does have mass, the handle, so they both rotate around a point that's definitely not at the center of the stick, and definitely not at the blade, it's somewhere in between. And so it's, when you gotta do a little bit more of the moment of inertia, angular momentum and stuff like that, and it gets a little bit more complex, you do have to understand the geometry. But for simple center of mass, you treat this mass as a point particle right there, but a massless ball. It's the same thing in terms of the math. You can do the math, but it requires calculus. And so this simplification makes it easy. And it's also another reason why I don't give you non-uniform bars. If we had calculus, I would say lambda over here is 100 grams per meter, lambda over here is 400 grams per meter. Where's the center of mass of the stick? Now you gotta know calculus. So we have to keep things simple. Does that answer? That's a good question, so. And once again, as a reminder, both today and tomorrow, tutors will be in the tutoring room from 1 to 6. So go and abuse them to your heart's content. So next question. Question, who's got the questions? If we can last a half an hour, then we'll leave a little early. Yes?
Could you do number 10 on the
Number 10 on problem set 5, I detect a trend, which is fine. Oh, so you're asking for me to, okay. Actually, fine, I'll do 9 and 10. Let's just see. Broke me down. It's because I'm so used to in tutorials, and I'm fine with it. Which one do you want me to do? Number 1. And then after that, which one? Number 2. And then it works. We got the time, and it really does help having you see these problems be done. In number 9, the stick does have mass, and it doesn't rotate. So the center of mass of the stick is at 0.4. You have a 1 kilogram mass at 0 and a 3 kilogram mass at 0.8. It's 400 grams per meter. So the mass of the stick is lambda L, or 0.4 times 0.8, or 0.32 kilograms. So that's the mass of the stick. And a lot of this information we're going to have to use again. We have to determine the center of mass. So center of mass is the sum of the positions. Oh, what was that? Sum of the positions multiplied by the masses divided by the sum of the masses. This makes it 0 times 1 plus the position of the stick center of mass, 0.4, times the mass of the stick itself, 0.32, plus the position, 0.8. Actually, that should be 0.8. 0.8 times its mass, which is 3. So this becomes 1 plus 0.32 plus 3. Oh, I can see what you're getting at for number 10, because we got to do something weird with it. That's 0. Let's see if I got this right. Because I get an answer of 0.22. I'm doubting it for just a moment. 0.4. Oh, I know what I did. Hold on. I made a calculator boo-boo and my brain was screaming at me. What did you guys get? All right, now I'm doing it. Because sometimes you look at these numbers and it's like, sometimes the calculator really respects the order of calculation. Okay. So it's 0.585 meters. So it's not at 0.6 meters, it is a little bit off. Now you have to calculate the moment of inertia of this system. So it's over here. Oh, and actually we're gonna, 9 is more complex than 10. So that's the rotation point. Now M1 and M2, this distance here is 0.585 meters because it's on one side of the length, or of the stick. This particular length here is 0.8 minus 0.585, or 0.215 meters. This distance here, and this is the trick of the whole thing, That's the distance from the center of the stick to its rotation point. And that is the value D. If this coordinate, that is the center of mass of the stick, and its coordinate is 0.4. Therefore, the distance between there and there is the coordinate of the center of mass, 0.585 minus 0.4, or 0.185 meters. That is the value D, and that is the hardest part of the problem. The moment of inertia is m1r1 squared plus 1/12 ml squared plus m stick d squared plus m2r2 squared. Plug and chug. So in this particular case of number 9, you do have to use the parallel axis theorem. You have to use the parallel axis theorem because the rotation point is not at the center of mass of the stick. Therefore, you have to add that term. So for number 9, it's like this. For number 10, the moment of inertia simplifies to this. And why is that? Because I drilled a hole dead center between the 2 points. So now I forced the system to rotate around the center of mass of the stick. So you don't have to do it in that particular case. In both 9 and 10, you use L equals I omega. Here, these R's are given here. In 10's case, R1 is equal to R2, which is equal to 0.4 meters. And L is equal to 0.8 meters for both. Now, these R's are not those R's. These R's are R1 is equal to 0.585 and R2 is equal to 0.215. And so those are the values that you plug in. And then L is the uniform I omega. Yes?
What does lambda represent again?
Lambda is the linear mass density. It's the linear equivalent of just normal density. There are many ways to express it, but lambda is the one that I typically go with. And so that's 9 and 10. It's just setting it up. They're all set up differently. 7 and 8, the stick has no mass. 9 and 10, the stick does. In 7 and 9, they rotate around their center of mass. In 7 and 9, they rotate about center of mass. 8 and 10, they rotate dead center. They're forced to rotate around the center. Okay. All right, next question.
Can you do 16 on problem set 5?
16 on problem set 5. Excellent. Okay. So 16 has no friction. Yay, no friction. In 16, the beginning position is this. the initial velocity is 0. Now obviously M2 is 20 kilograms, M1 is 3, so which way do we think this thing's going to go? M2 is going to fall. I'm going to make it obvious in all the Atwood's energy problems. So the initial potential energy, if this starts at height L, this one starts at height little l. At the end of the motion, that one is moving with the velocity v. That one is also moving with the velocity v. The question is, I want to find that final velocity. So what do we have to think about? We have to think about the energies involved at the beginning and the end. The easiest part is understanding that at the beginning it's not moving and at the end it is moving. So at the beginning, the initial kinetic energy is 0. The final kinetic energy is just 1/2 m1 plus m2 v squared. Both of them are moving. Both of them are moving at the same velocity. Now comes the real tricky question. This one falls a length L, so the potential energy initially for 2 is m2gl. The final potential energy for 2 is 0 because it's resting at the bottom. There's no more change. Now, one of the things that we need to really look at, and this will help with problem 14, is just looking at M1 for just a moment. This is the height L1. That's a height that we don't know. It moved up a length L. Now this angle theta is the same as that angle theta, which is 40 degrees. This new height that height there is merely L1 plus L2, where that is L2 and that is L1. Actually, we're not using little L2 over here, so I'm going to use little L2 over there. The initial potential energy over here is M1GL1. The final potential energy for 1 is M1GL1 plus L2. The change in potential energy, which is all we're really caring about, is M1GL1 plus L2 minus M1GL1. The bottom line of all of this, it's not important to truly know the starting height of the object or the ending height of the object. What is important is the change in height. So the potential energy of 1 increases by a value of M1GL2. So when we're putting all of these things together, now technically there could be an M1GL over here, an M1GL1 over here, and an M1GL1 over here. But they cancel each other out. All that we're interested in is the increase in potential energy. Now this becomes M2GL minus M1GL2 equals 1/2 M1 plus M2 V squared. So this becomes 2 M2GL minus M1GL2 equals M1 plus M2 V squared. Now, what I'm going to do is I'm going to substitute for L2. L2 is not a quantity that we know, but we can figure it out. L2, if we think about the sine of theta, and we know what theta is L2 divided by L. So L2 is equal to L sine of theta. So this becomes 2 M2GL minus M1GL sine theta is equal to M1 plus M2 V squared. Solve for V. There's a common factor of GL in both of these, so it becomes 2GL M2 minus M1 sine theta divided by M1 plus M2 V squared 2GL is equal to V. And so that's how you solve it. Now it's just plug and chug. So the first thing you had to do was identify the energy states. The initial energy state, M1 was at a height L1. We didn't know that. M2 was at a height L. We do know that. At the end, this is moving at velocity V, and this height here was now L1 plus L2. We then had to sit and figure out that the change in potential energy is what we really needed to know. If I move from there, this sheet of paper from here to there, the change in potential energy is the same as from there to there as it is from there to there. If the starting conditions are the same and the ending conditions are the same, the fact that one started over the table and the other one started over the floor, it's merely their change in potential energy that's the important part of the problem. And so that's part of the trick. Now it's the same thing with 14. We won't do it much, but you could say that there is an arbitrary height Q. So the initial potential energy is M1GQ. Well, what's the final potential energy of M1? The final potential energy of M1 is M1G big L plus Q. So what you do is you find out that there is an M1GQ on one side and an M1GQ on the other. Then they cancel each other out, and then all you're really caring about is the difference. So it's the change in potential energy. How much potential energy was stored into M1? And that's the gist of number 16. Because that's the variant of, there was one test problem, not given by me, but given to a Cal-based physics. It was this. It was like mass 1 on one side, 2 inclined planes. They had friction, and the class just lost it. And I'm like, when you sit there and think about it, you've got to be disciplined. And granted, I'm not going to throw that at you on a test or on a final, but you just have to sit there and think about the parts. What is the state, potential and kinetic at the beginning? What is the state, potential and kinetic at the end? Once you've got that, then everything else flows together. Okay, next. So if we can go 7 more minutes, then that'll be it. We can do what are the units of spring constant? Oh, we're gonna have like an oral quiz right now. Let's go have this, unless I can come up with the questions. Newtons per meter. What law determines a spring's stretch distance with how much force you put on that spring? Hooke's law. Okay. In vector notation, what is Hooke's law? How about in magnitude? What is Hooke's law?
Equals kx.
F equals kx. In vector notation, what is Hooke's law?
Equals negative kx.
And which ones are vectors? F and x, yes. Is k a vector? No, k is simply a magnitude. Express radial acceleration in terms of just your general variables.
V squared over r.
V squared over r. What are the units of V squared over r? What is V squared over r? A type of blank. Starts with A. Acceleration. What are the units of acceleration?
Meters per second squared.
Meters per second squared. What is the fundamental unit for time? Seconds. What is the fundamental unit for mass? Kilograms. How many grams in a kilogram? 1,000. Express it in scientific notation. 10 to the 3. Yeah, you gotta sit there. See, this is all like now what I'm trying to get you guys to do is be on some type of science hole and just go up against high schools. Units of coefficient of static friction are what?
There are none.
There are none. What's the difference between static friction units and kinetic friction units?
There's no difference.
Sometimes the answer is there's no difference. And actually what should happen by the end of the summer is you should start speaking to me and answering with a certain tone of insolence. Like, how dare you ask me that question? I will start respecting that even more. A is towards the ceiling. B is towards the front of the class. What is A cross B? A is towards the ceiling, B is towards the front of the class. That means B points this way. A cross B equals blank, B cross A. Negative. Units of momentum. Kilograms, meters per second. All right, you're not getting it. Inelastic collision. What quantities are conserved? An inelastic collision. Is it one quantity or two? And it's two, name them. It's one, name them. So you gotta have to start knowing this. Inelastic collision, what's conserved? Momentum. You could be starting and say mass, but momentum only conserved. Energy is conserved only during what? An elastic collision. Now remember that the energy that we use versus the energy that they use in lab, they prefer to call it mechanical energy. We just use energy. They use mechanical energy because they're real snarky over there. Because if they say, question in lab, is energy conserved in an elastic collision? The energy that they're referring to is the energy of the universe. The energy that we use here in the room is effectively mechanical energy. So if they get cute on you and they say energy, ask them, do you mean mechanical energy? And then they say no, and then you know the trick is on, and they're going to try to get you. What are the units of angular velocity? You said meters per second? No. Your tone is almost approving, but no. Radians per second. Technically, is radian a unit? No. So if we're going to be technical, if we're going to be total OCD about this, which we're not in this class, I will accept radians. What's the way that you express angular velocity? Yeah, inverse. You can just say inverse seconds. That's why angular velocity is frequently called angular frequency, because the units of angular frequency are inverse seconds, which is typical of what we think of as normal seconds. Or I'm sorry, normal frequency. That's it. I'm tired of you guys.